Hello, thank you for watching this video and studying math with me. Today our topic is going to be absolute value equations and inequalities. We're going to begin by establishing some fundamental principles about absolute values, equations, and inequalities. So let's begin this way. And in what follows, we're going to be assumed that p is a number that is bigger than or equal to 0. So recall that the absolute value function describes the distance that whatever we put in between the absolute values is from 0. That means that if I were to say that the absolute value of z is equal to p, that means that z is exactly p units away from 0. So z could either be plus or minus p on the number line. It could go either way, right or left, and so z could be plus or minus p. Similarly, if we assert that the absolute value of z is less than p, that means that z is less than p units from 0. So it can be, this point is not included. There's an open circle here. So z has to come from these two areas from minus p up to p, not including the endpoints. So we can conclude in this case that minus p is less than z and z is less than p. So that is the and condition. If we were to consider the absolute value of z being bigger than p, that means that the distance from 0 to where p is, or where z is rather, is going to be more than or equal to p. So I could be out here, or I could be down here, and I use the word or, and that is important. That means that z is either less than or equal to minus p, or greater than or equal to p. If we have an expression where the absolute value of z1 is equal to the absolute value of z2, that really means that z1 is either equal to z2 or z1 is equal to negative of the whole of z2. And finally, we have some special cases. We do know that the absolute value of z is always greater than or equal to 0. That means, for example, if the absolute value of z is equal to 0, then z is equal to 0. Z is never negative, and it is always bigger than or equal to 0. So we're going to talk about these several rules as we go through and solve the problems, and I'll try to make reference to them by number. So here's the first example that we'll do. We have the absolute value of 9 minus 4x is equal to 7. This corresponds to the rule I talked about called number 1, where the absolute value of z is equal to p, and so that means that what I will do is I will say that the role of z here is being played by 9 minus 4x, so either this is equal to 7 or that is equal to negative 7. I solve them each in turn. I maintain the or, and that means that either the solution is x equal 4 on this side or x is equal to 1/2 on the other side. Our solution set then is going to be 1/2 and 4. Those are the only two answers for this problem. The next problem that we're going to look at is again solving an equation. Well, we have the absolute value of a z1 is equal to the absolute value of a z2. This corresponds to rule number 4 the way I described it. So what we conclude is that z1 is equal to z2, or, again it is or, z1 is equal to the negative of the whole of z2. Notice that this is minus x minus 5. I solve them each in turn with an or in between. Here I get that x is 3/4. Here I get x is minus 7/2. That means that the solution set has two elements in it. The answers are either minus 7/2 or 3/4. Now we're moving to solving absolute value inequalities. Here you see it is a less than inequality. This corresponds to the rule number 2 that I talked about earlier, the absolute value of z being less than p, and that meant that z was caught in between minus p and p. So here the role of z is being played by 4x minus 6, so that means that 4x minus 6 is between minus 10 and positive 10. I can go through and solve this and get that x is between minus 1 and 4. Now if I graph that, the endpoints are not included. It's everything in between. And in interval notation, I would write this as open parentheses, -1, comma 4, closed parentheses. Often I will ask you to write your answers in interval notation. The next example is again solving an absolute value inequality, but this time it's the absolute value of z is bigger than 10, or the absolute value of z is bigger than p, as I was talking about in rule number 3. So this is going to give us an OR condition. So either z, what is between the absolute values, is bigger than 10, or whatever is between the absolute values less than -10. And there's an OR in between. So I will work through and solve both sides separately. Here I get z is bigger than 4. That means I'm on this part of the number line. Or z is less than -1 on this part of the number line. To write this answer then in interval notation, it's going to be from -1 up to -1, open interval, union. This union sign we learned in chapter R meant OR in math language. And then we have the set beginning open interval at 4 up to positive infinity. So that's example 2b. Now example 3 is called solving absolute value inequalities requiring a transformation. You see, this is not of the form yet where the absolute value of z is bigger than or equal to a number. You have that 6 in the wrong place. So first thing we're going to do is subtract the 6 from both sides, and now we have something that we can deal with. This again is rule 3 as I specified. So now whenever we have this, the role of z is being played by 5 minus 8x, and that means that 5 minus 8x is bigger than or equal to 8, or 5 minus 8x is less than or equal to -8. I solve these both in turn and find that x is less than or equal to -3/8, or it's bigger than or equal to 13/8. That means either I'm up here on the number line or I am down here. Again, those are split, so I have to use the union to represent the OR. In interval notation, I would go from -infinity up to -3/8. The bracket meaning that -3/8 is included. I begin here, bracket 3/8, that means that point is included, going up to positive infinity. The next problem that we're going to talk about has the absolute value of 7x plus 28 equal to 0. The only way that can happen is if 7x plus 28 is exactly 0. That means that x is -4, and that means that is our solution set. That's one of the examples of special cases. We're going to be talking about other special cases as well. Here's the next example. We're saying the absolute value of x minus 9 is bigger than -2. Well, the absolute value is always bigger than or equal to 0, so it's always going to be bigger than or equal to, or bigger than, in fact, -2. And so that means this is always true. That means our solution set is, in interval notation, any number from -infinity to positive infinity. The entire number line is full of solutions. So any real number will work there. The next example, another special case, says the absolute value of 2 minus 5x is less than or equal to -5. How often is the absolute value negative? The answer is never. This is never true. So the solution set is the empty set or the null set, and sometimes this notation is used to denote the empty set or the null set. Now, absolute values do have applications in describing distances and also in describing tolerances. Let's look at a couple of examples here called example 5. So suppose I say that m is no more than 9 units from 3. That means the distance from m to 3 is no more than 9. That means it is less than or equal to 9. So here I'm using the absolute value to describe a set of words. If I say t is within 0.02 units of 5.8, that means that, now here I'm within, that means I could not be 0.02, I'm within that tolerance, so here it is t minus 5.8 is less than 0.02. We can also use the absolute value to model tolerance. What kind of accuracy do we really need? So suppose that we have 5x minus 2, and we want, that is what y is equal to 5x minus 2, and we want y to be within, let's see, that is tenths, hundredths, thousandths, 1,000th unit of 6. So what values of x will do this? We do this a lot in calculus with the epsilon delta proofs. So we start with this, we use these words, we want to be within that distance of this from 6. So we set up that absolute value, but now we can simplify this. This is going to be 5x minus 8, and that has to be less than 0.001. Now, here I have the absolute value being less than a number, so that means this number is bigger than or equal to the negative of that number, there's z, and less than the positive of that number. So first I can do is add 8 everywhere, and then divide by 5, so I can include x is in between this number and that number, or in interval notation I'd have open intervals on both sides. That is the solution set. That's the end of the examples. You do have some homework to do, and remember that time is precious. Each day must count. Do the math. It will make you strong. Take care.